Hey everyone, today we'll be going over a full walkthrough on building an unbalanced tree, and without any further hesitation, let's get started. And now let's focus on inserting a node into an unbalanced tree. So, to be able to kick things off, what I'll be doing is that we will be importing our library. So we have include iOS stream. So we'll have Q stack and TreePrinter file that we have, and we'll be using namespace std. I have a class called binary tree in a public instance. We're going to construct our nodes. Int key node to the left, node to the right, and initialize our node int k key k left null pointer, right pointer will be set to null. So we initialize everything. Node root binary tree root null pointer, and node insert node int key, and we will be doing a boolean condition of if we're not at the node, then we will return a new node with the respective key. And if the key is less than the node specifically at the key, then we will insert at the left, node left equals insert node left key. Otherwise, we will insert right equals insert node right key. And finally return the node. And now we will import our, make sure that we have our semicolons already set up in place. There we go. Make sure we have everything set up, all cleaned. All right, now we will have our main function, binary tree, bt, TreePrinter, and then we'll have bt root equal bt with the function that we just made, insert, and we'll have the root that we're importing, and then specifically 10, and this time we'll put 5, and count nodes inserted in the unbalanced tree. And then we will do printer print pretty bt root one 0. And finally, as our base case, we return 0 in the main function. So, there we go. Make sure it's all good. All right, let's run this thing. And the nodes are inserted correctly in the unbalanced tree. And now let's head over to remove a node from the unbalanced tree. And now we will be focusing on removing a node. So in order for us to be able to remove a node, what we need to do is that we need to do what we did before, as previously when we were working with the balanced tree. Since we are checking in particular on the following root, what we will be doing is that we will have a check with the current node, and then we will delete a node. So this is how we do. we are going to be doing node, min, value, node, node, node. And while we initialize the current node to be the node we are looking for, we are going to be searching through and looping around current and current on the left-hand side is equal to the null pointer because we're just initializing left, and we'll have current equal current left as well. Finally, we will return the current node we are at, and then we will delete a node, and we're going to be doing so by the following node function: node delete node, node root int key, and if it's not at the root, we return the root. And we'll be doing a series of checks to determine if we're at the following. So also we will return root, there we go. So if the key is less than the root data point at the key that we're looking for, the root on the left hand side we will go for root left key, else if the key is greater than the root key, then that means we go to the right. So root right equals delete node root right key. And then otherwise we will do the following: if the root at the left is equal to the null pointer, we will have a temporary node, right, and we will delete the following root and return the temp, so that we know exactly what we are going for. And else if the root on the right is equal to the null pointer, we initialize node temp equals root at the left, and then we will delete the root as a placeholder, and then return the temp. And then we will have node temp equal min value node on the right, and root key equal the data point of the temporary node. And then we will go for the right hand side to delete the node root right temp key as those parameters. Return the root, yep, that's what we do. Now we're going to go down and we'll be doing the following function. We will be doing bt root equal bt dot delete node, and I'm going to go with the root that we have, and I'm going to select 20 to delete. Node deleted from the unbalanced tree, and then we're going to print our updated tree that we have. Make sure build everything, and here we go. Yep, and we have done so already. So this was deleting a node from an unbalanced tree. By doing the following: we check where we're at, and then we focus on deleting the node by doing a series of checks and balances to determine where the specific node is at, and we deleted the following node accordingly. And now performing in-order traversal for an unbalanced tree. So in order for us to be able to do so, we are going to be creating a void function called in-order, and then have node be the root be inserted as a parameter, and then we're going to have if we're at the root, then we will do the following. We are going to call upon our in-order function to get the root on the left. We're going to output the data root key, here, and in order of the root to the right. And then what we will be doing is that we will be outputting our in order traversal, and we're going to be doing count in order traversal of binary tree, and then BT in order of BT root. That should actually be able to get us already set up. Yep. And in fact, let me just clean this part up. There we go. So yes, so we have in order traversal of the binary tree with 5, 10, and 20. That's what we have done. We go to left, top, and then right. Much like in the case of what we did for the balanced tree, except for we're just putting this in the unbalanced tree. And now going over pre-order traversal. So pre-order traversal will be the following, much like what we did in the balanced tree, except for we're putting it inside of our unbalanced tree, but the principle still applies. So we do go void pre-order node at the root, and then we will be checking, much like in the case of what we did before and what we did previously, if the root will output the count root key right there, and then we do pre-order with the root on the left, and then the pre-order with the root on the right, and make sure it's already built. Yes, it is. And now we will do the same thing that we did before. We do in order traversal, and then we're going to do pre-order traversal. Let me just clean this up. Pre-order traversal. Pre-order traversal with the following root. Make sure that we have everything already set up in place. And let's run this bad boy. Alright, and I'll just clean this part up. There we go. So yes, it does what is accordingly. So it goes 10, 5, and 20, much like in the case. 10, 5, and 20 in the pre-order fashion. So we already see that is the nature of pre-order. Now let's move over to post-order traversal. And now going over post-order traversal, so what we did, we just left off from our pre-order and we just moved up all the way to our post-order section inside of our class that we have done thus far for an unbalanced tree. And the way we're going to be writing our post-order is going to be the following, much like in the case of what we did before for the balanced tree, but we're just putting it inside of the unbalanced tree. We go void post-order node root. If we're at the root, then we're going to go post-order root at the left, and then we'll go to the right, and finally output data root key right over here. That's what we do. And now we have our function right here. Let's output the post order. So we're going to do what we did before. It's post order, and bt dot post order. BT root, let's just build this, make sure it's all good, and I'm going to say unbalanced, just for sake of clarification. They're interchangeable for what we have, because we're not dealing with a binary search tree. There we go, for the sake of simplicity. There we go. Yep, it does so accordingly. So we have 5, 20, and 10. We see in our tree 5, 20, and 10, going by each level accordingly. So we see the nature between all three of the different traversals in an unbalanced tree. Now let's head over and do our breadth first search for an unbalanced tree. And now I'm focusing on breadth first search for our unbalanced tree. So the way we're going to go about this, remember, from what we have already done in our balanced tree, breadth first searches differ from depth first search because breadth first searches uses a queue and go based on level. So we need to make sure that we have our necessary libraries. Yes, we do. We have a queue and a stack already set up in place. And there are also tiny circles that go directly, that are being circled from the left-hand side to the right, so that way we see the order of what we're going. So first thing we're going to do when time this out is going to be void breadth first search with node at the root, and then if we're not at the root, we're going to return, and we're going to have our queue, node queue, call this queue dot push with the root, and while the queue is not empty because we put a root in, we're going to do the following: node at the front, because queues go in, first out, count node key, output in data, and then we're going to pop the queue just to indicate all the data that has already been pushed out. Yeah, and then we'll go directly from the left-hand side with if the node is at the left, we're going to go queue.push node left. We'll also do the same thing for the right. There we go. Yes, yes, and yes. That's how we develop our breadth first search over here. And now we will go over our breadth first search. We do so based on the following: count /n, just to make sure it's all spaced out. Breadth first search of unbalanced tree. We're going to go bt.bfs with bt.root. And then alright, it's built successfully. There we go. Breadth first search of unbalanced tree. That's going to be 10, 5, and 20. Breadth first search, a good way of thinking about it. There are tiny circles that are being that are invisible but are there, that are going to be circling all the way from to the left all the way back to the right, and hence we already have the output of 10, 5, and 20. It's a good exercise to be able to see exactly how the breadth first search is already conducted, because it goes based on level from the root all the way to the other children as well. And now let's focus on depth first search. And the way we develop depth first search is much like in the case of what we did for the balanced tree. And also keeping in mind, for depth first search, we use a stack. And a good way of thinking about depth first search is just thinking of a giant circle in general of the way how depth first search is already going compared to breadth first search. Breadth first search focuses on levels, so breadth first search would technically have tiny little circles going from the root that are being drawn from the left to the right, much like in the case over here. But for breadth first search, they're more so giant circles to keep in mind. So if there was, for instance, more children on the left-hand side, we would see, for instance, more of an encompass on the left-hand side compared with the right, but we're still going in this fashion of one giant circle compared to breadth first search, where will be tiny circles of levels. But anyway, we developed depth first search by doing the following: void depth first search node here root, and then if we're out not at the root, we return. Then we will have stack node here with call to s, and I'm going to push the root into the stack so that while the stack is not empty, we will have the following nodes be pushed, or stacks in general, they're like a stack of plates, so technically we would have the stack already situated at the top. So we will have node equal s.top right here, and then we'll output the data, node key. Righty. And then s.pop. And then if we are node right, the order is also very different compared to what we have over the left. So we have the node at the right, And we're gonna go s.push. Yeah, node at the right, and then if the node at the left, we're gonna s.push node to the left. There we go. So that's depth first search over here, in contrast with breadth first search. And what we'll be doing, we'll be going down, much like the case of what we did before. So instead of breadth first search, we'll go depth first search. Depth first search of unbalanced tree, and we just got to do this function right here, bt.dfs, bt.root, and we should get the following. Yep, that is correct. 10, 5, and 20, much like in the case of what we have over here, 10, 5, and 20. And yeah, that was depth first search for our unbalanced tree, much like in the case in the fashion of what we did for the balanced tree, except where we put it in unbalanced. An unbalanced tree can be considered a binary tree in this case and in general. So yes, this was depth first search. And now just going to go over what we have already fully accomplished in our unbalanced tree. So we have already included our libraries using namespace std for the sake of convenience. We have a class and a public instance for our nodes. We have our root. We also have initialized our root as well. We did our insert as well. And then we removed a node. We checked where we were for the current node, and then we looked for in particular of our node that we are starting particularly from the root and its data point for the key. We are looking in particular through the root. We initialized at the top, and we're going to use that as a starting point to go through the left and the right side when searching throughout the rest of the tree to either insert from what we've already done, and then moving over to delete. We check the right and the left hand side, and then we also check in particular on if the root has already been deleted. Well, technically the node that we are searching for, but we call the root as that starting point that we are searching throughout the rest of the tree. We perform in order traversal, as we have already stated, 5, 10, 20. If we have already set up in place. We've also done pre-order as well, where we focus on the left and the right. Notice in particular pre-order traversal of an unbalanced tree, 10, 5, and 20. Post-order as well, we do the left, then the right, hence going 5, 20, and 10. Then we did breadth first search, and we always use a queue for such. We would typically have the same output that we have, but the key differences is the fashion and order of how searches are conducted. So breadth first search goes by level. So for instance, there's a small circle at the top and smaller circles as well being drawn from the left to the right, or to the left all the way back around from the right. And depth first search, on the other hand, uses a stack, and we use the functions for the stack to be able to keep track of everything that we've visited. And depth first search can be thought of as a giant circle that is going around the whole tree, starting from the root to the left, to the right, and back again. And this is critical for other subtrees as well that could be inside of the unbalanced tree. So yes, this was our unbalanced tree. I will put the following code in reference as well, but yes, this is what we have accomplished for the unbalanced tree.
Hey everyone, thank you very much for taking time to watch this. If you found this video helpful, be sure and feel free to please like and subscribe. And if you have any other questions or suggestions, please put them in the comment section. And as always, take care. Cheers. Bye-bye.